The distance between those capacitors doesn't matter when it's in series, right?
It doesn't, I mean, in an ideal world where the wire didn't have any resistance or anything, then it wouldn't matter. In real life, yeah, it does.
So like I'm talking like on the homework.
On the homework, no, it does not.
I didn't think so.
So,
I didn't think so.
okay. So, okay, it says, what's the charge on capacitor C1? Let's find out what all we got here. Capacitance. Okay, so we got let me write all this crap down. So 6.1, 2.95, 4.7. So that's going in series, or sorry, in parallel. And it's coming down here and having another one in series. So it was 6.1 microfarads. What were the other ones? 2.95 and 4.7. And I quit writing again. And I forgot what it was. 4.7. And then it says when it's all hooked together, the charge on this one is 40 microcoulombs. Okay. So for what all does it ask? I know it asks the charge on C1, the charge on, oh no, the charge on C2 is 40. Okay, I'll have to change that. So we're looking for charge on C1, charge on C3, and the applied voltage. So this one has 40 microcoulombs. Okay, so again, if you just think about these two formulas, it's actually still kind of hard. But if you think about why they were true, then it's really easy. Because if I look at this top circuit, well, the potential drop across the bottom has to be the same as the potential drop across the top, right? So if I look at the potential on the bottom, again, F is Q over V, so V would be Q over F. So the potential drop across the bottom is 40 over 2.95, which has to be equal to the charge on the top, which is what we're looking for, over 6.1. Right. Grab my calculator. So I have 6.1 times 40 divided by 2.95. So apparently I've got 82.7 coulombs on top, or microcoulombs on top. Yeah. All right. Okay. On capacitor C3, well, again, if I think back to why this was true, when you have these guys in parallel, the charge on the first capacitor has to be the same as the charge on the second capacitor, or else it would kind of split up and even out. So if I kind of imagine this guy as being one huge capacitor, how much charge does it have on it? I mean, just this top little circuit. It's one of those questions that's so simple, it's kind of hard. How much charge am I storing in this
Like
circuit?
here.
What? Oh, okay, sorry. You should tell me when that happens. Let's reconnect real quick. Well, you can do it. Okay. Should be coming back up. Okay, so imagine this little top circuit here as being one huge capacitor. Then how much charge am I storing on that capacitor? I've got A2 on the top part plus another 40.
122.7.
Yeah, 122.7. And since this is in series, the charge stored on the second one has to be the same as the charge stored on the first one. So
So the one on the bottom is the same as stored on the added to, or just?
Okay. Let me go back. So again, if you look back at the series thing, I mean, if it really was just two capacitors straight like this, if there was any extra charge on F2 or any less, you'd have charge moving between the F1 and F2 until they balanced. Here, the picture is more complicated, but it's still basically the same thing. If I had any more or less charge on the top part than I had on the bottom, then I would have electrons moving around the wire until it evened out. So since the total charge I've got on this top circuit is 122, that means I also have to have 122 charge stored on the bottom capacitor. Okay. And then last one, what is the applied voltage? So, whoops, wrong one. So again, the net charge is still, so I guess the last thing to say is that we did this when we did this series one, but I didn't actually ever say it. Notice we didn't like add these two charges together when I found the capacitance of the whole thing. I still just said, oh, it's just Q, even though there's really Q here and Q there also. That's because the middle ones kind of cancel out. Because I've got.
From where are you talking?
Okay. Okay. Well, let me just answer the question, and then I'll tell you why I thought it was tricky and worth saying something. But maybe I'm just being silly and it's not really worth saying something. Okay. Right. Damn it.
I want you to type.
I know. There we go. So F is, okay, Q over V. The Q is the 122.7, right? And that's what I wanted to say. The Q is 122.7. It's not doubled it. I mean, you don't count the 122 up here and the 122 down there if they're in series.
I got you.
Right. And then for the potential difference, well, I guess you could do this one of two ways. We need to either find the capacitance of the whole thing and then use that to get V, or we could just find the individual V's and add them together. What do y'all want to do? It really does. It's about the same amount of work either way.
Yeah, probably easier to find the individual equipment.
Okay, so if we find the individual V's, well, the V on the top was this 40 over 2.95. So the potential drop going across the top is that, plus the potential drop going across the bottom, which again, if you get V by itself, V is Q over F. So on bottom, I go 122.7 over 4.7. So that's the potential drop across the top plus the potential drop across the bottom. That'll give you the potential drop across the whole thing.
And since the top part is together, you don't You don't use that 40 or 2.95 twice.
No. Because, I mean, if you think about, I mean, current is actually electrons moving or whatever. If I think about one particular electron's life, it only goes across, it might go across the top or the bottom top. But either way, it's only going to go across one of them. So, yeah, you only do the potential drop for one of them. So plus 122.7 divided by 4.7 is 30.6 or 30.7.
That was 39.
Oh, 39.7. You know me and my ability to read can be a little.
I almost didn't say that.
Just so I can miss it. Hey, I don't lose 8 points when I miss them.
I have noticed. I have noticed. You should make ours that way.
Let's jump over to university and do one of those. I guess while we're moving, talk just a second about what capacitance is used for. I mean, it's kind of what it sounds like. If you think capacity, that's like how much you can store. And what capacitors are really used for is to store charge. Whereas, people, I mean, it's very common to think, oh, it's kind of like a battery, right? It's like, no, batteries really create a potential difference. They're more of an energy thing. Capacitors, you can kind of use them like a battery, but what you tend to use them for is to store charge. Like if you actually need.
I use them on pivots on the phone.
Use them on pivots?
Yeah.
Okay.
That way, if for some reason it needs a little extra juice, that's all there.
Yeah.
Use them on those. It's not to give them the power. It's
more
sound systems in a car is even easier to explain.
Okay.
A capacitor on your sound system in your car, your lights don't dim when it pulls the juice because it's pulling off the capacitor, not the battery.
Right. Yeah, capacitors are really more like if you need a quick burst of energy instead of like a continuous source of energy. So the example I usually give is like the light bulb in your flash or something where, I mean, your camera doesn't need that power except for that one split second. And so the capacitor discharges it. And then the battery turns around and charges the capacitor on the flash again. But, okay. Cool. Let's create one more section of this.